No, I'm not going to smash the place up. Although if they don't have donuts at Cloud and Bakery at about 4 o'clock in the afternoon on a Saturday, well, maybe I should consider it. I mean, it used to be the best bakery in, you know, the southern suburbs, if not the southern part of Australia there, you know. You could always get breakfast of champions late in the afternoon there. Not only on a Saturday, but even during the week as well. And what are the tourists thinking? That's what I want to know. Anyway, this is why they call us nutters. Because basically, if you number your hexagon nuts with numbers, you can put them on the screw thread. But you can actually line them up such that you get two lines, 6x plus 1 and 6x minus 1. Yeah, so there you go, you got your, there's your 6. So you line up, so all the, sorry, where's the 6 gone again? 4, 5, 6, 12, and like that. So all the 6's line up, and then you'll find that on either side of the 6, you have all your prime numbers, but not all those numbers on those two lines are prime, but all your prime numbers do exist on those two lines. In other words, they exist in a very localized part of mathematical space. Yeah, something like that. 6, 12, 18, and on the side you have 1, 7 and 13, and on the other side you have 5, 11, 17, and it just goes on and on and so forth. That's because your double primes never get closer than 3 between each other, or 6 between the actual centres of the two double primes. I don't think I made that point too clear on the last upload in the written section, I think. Anyway, so let's see. Now what's the next one? 18, 3 8s are 24, 3 6s, 6 4s are 24, and then on that side you've now got 7. I don't know if you can see this. 7, 13, 19, and on the other side of the 6 you've got your 23, and so forth. So there you go, that's your answer to your prime numbers. You got your two lines going off to infinity, so as the numbers get bigger and bigger, both numbers at the end of the two lines are getting closer and closer towards infinity, but they're also both very massive, and they are a distance of 2 from one another. So there you go, you got the number 2 coming into prime theory then. Do you get that? Now if you look at the horizon, I don't know, if you go out there and look at the horizon and something going off to the distance, and you've got two parallel lines going off into the distance, they don't actually go off to infinity. They meet and form the end of a parabola. That's what I'm trying to get across. The idea is to solve the idea of infinity. Maybe that's what Archimedes did. He realized, he actually noticed, to see what you actually see is if you've got like parallel train tracks or other sort of parallel lines going off into the distance, and it's really obvious when you have a reflective medium like a lake or something like that, and you've got some sort of reflection going on. Then you've got two parallel lines coming from the top and two parallel lines coming from below, and you realise that they actually meet, but they meet before the horizon, and they meet in a parabola like cone or shape at the end of there. So in other words, it's implying that those two parallel lines are not actually parallel. Do you understand what that means? So we don't really, it also means that we don't really have straight lines in perspective.